Oftentimes it's advantageous to carry out double integrals using polar coordinates. As a refresher on polar coordinates, here we have the point xy, which we may instead discuss using the variable r, one of the variables of polar coordinates, and it's the distance away from the origin to the point. And here, in our setting, r will always be positive. And the other variable used in polar coordinates is theta. And theta is the angle between this line and the positive x-axis. So theta is always the angle that we create winding up from the positive x-axis as we move along in a circle. And so theta is between 0 and 2 pi in our setting. Here are also some formulas that will help you to get r and theta if you start with x and y, and to get x and y if you start with r and theta. One should use caution when using the arctan function, since points in the, say, first quadrant and third quadrant may give you the same theta if you just plug it in the calculator naively. So you have to be careful and peel your eyes. So suppose, for example, you have in the third quadrant minus y and minus x. Well, the minus signs cancel. And so you plug that in a calculator and it would give you the same answer as if those x and y's were in the first quadrant. So be careful and use caution when using the arctan function. We may also describe regions in the plane using polar coordinates in the following way. So here we have r between a and b, and you could see that a extends to in blue there, and b extends from the origin out to the end in red there. Also, theta being between alpha, which is the angle here, purple, and beta, which is the angle here in green. So, what does this region describe? It describes what you see highlighted there. Moreover, beta minus alpha, so the bounds of theta, should be less than or equal to 2 pi in how we're using it in our setting. Sometimes it could be confusing getting the region described in terms of polar coordinates. Always remind yourself, if I'm a point in this region, what bounds must I obey? For example, here, if we just look at r being between a and b, in fact, many points respect the r being between a and b. You would end up getting a donut in that case. What causes us just to look at this region here is also the angle, the bounds on the angle. So if I'm a point in here, I must respect two things. One, that the r is between a and b, and the theta is between alpha and beta. And that's what you could ask yourself. What must I respect to stay in that region? To get some more practice with describing regions in terms of polar coordinates, let's see what happens as we vary, for example, a. So decreasing a, increasing it, decreasing b, increasing b. Of course, b should always be greater than a. Likewise, we could vary the angle. So if I increase beta, you could see here that I could go all the way around to 2 pi and get this donut. Likewise, we could vary alpha, where we start out, and here we're increasing alpha. And so this should give you a little bit more insight of how to describe regions in terms of polar coordinates. So if we wish to use polar coordinates, then we have to break up our region of integration into polar rectangles. Okay, here's your regular rectangular coordinates. You just break up the region into small rectangles with sides dx and dy, and so your area element at the end of the double integral is dx dy or those two in reverse order. But when we integrate using polar coordinates, we break up our region in these polar rectangles. And so what area should we use at the end of the integral? How should dA look? Well, what is the area of that that polar rectangle? We have this width, dr, if you want to think about the dr in terms of a width, and we have this outer arc here, and it has length r d theta, if the change in angle for describing that polar rectangle is d theta. So what about multiplying these two lengths together to get the area? So we have dr times r d theta. And here, for some intuition, recall that d theta doesn't have units when you use it for physical applications. So if dr does have units, that's meters right there. R has units, it would also be meters. D theta, no units. So we do end up getting a meter squared when we use this. And the area of this, as we take limits, okay, so as this polar rectangle gets smaller and smaller, then dA for that polar rectangle, the area of that polar rectangle, could be given by that expression there. Now, of course, one may object and say, well, this radius here is going to be different than the outer radius. That's absolutely true, but we're taking, as you take the limit to an infinitesimal polar rectangle, then this expression becomes accurate. So here we have the theorem for how to change variables from xy to polar coordinates. You could see here we have bounds, alpha and beta, a and b. Those are bounds for r and theta, respectively. And you could see how they show up in the order of integration there. So dr is integrated first, and so we have the bounds of r here, and d theta second, and we have alpha and beta, the bounds of alpha and beta next. What do we do about the x's and y's that we had in our integrand? Well, wherever you see an x, substitute r cosine theta there, and wherever you see a y, substitute r sine theta. And where is this guy coming from? What is that r? Where did that come from? That comes from our area element that we discussed above. So this is how you will carry out converting the problem of double integrals in rectangular coordinates to that of polar coordinates. So let's take a look at an example. Here we want to find the volume of the solid bounded by the paraboloid and the xy plane. Thus, we would like to find the volume of the solid that you see there. In order to get our region of integration, we'd like to see where the paraboloid here intersects the xy plane, and so we set 9 minus x squared minus y squared to 0. That's where the xy plane intersects the paraboloid, and you get this expression there. So the paraboloid intersects the xy plane at a circle of radius 3 in the xy plane. Thus, our region of integration will be that circle of radius 3, but also including points inside the circle. And we would like to describe this region. If we use x and y coordinates, here's one way to describe the region. So we could have x being between minus 3 and 3. And then y would have to be between the top part of the circle and the bottom part of the circle. So setting up that double integral, we'll get this expression here. Now, this expression is not very simple to integrate. We could do this much more easily if we use polar coordinates. And how do we know that? Well, for one thing, the integrand has 9 minus x squared minus y squared. So that could be described this way, and we now see this x squared plus y squared in there. That should give us a hint that perhaps we should change coordinates and substitute, instead of x squared plus y squared, just 1r squared. Okay? So that's one hint. Looking at the integrand seems amiable to using polar coordinates. The second hint comes from the actual region of integration. The region of integration is circular, and it is natural to describe circular regions in terms of polar coordinates. Thus, due to these two motivations, we'll choose to convert to polar coordinates. And let's see how to do that. Ingredient number 1 for converting to polar coordinates is to describe the region in terms of polar coordinates. Now, we had the circle of radius 3, so what you see here is the description in terms of polar coordinates. Our r is between 0 and 3, and our theta is between 0 and 2 pi, giving us the circle of radius 3. Next, let's look at the second ingredient. Here, we convert the integrand or function to polar coordinates. So here is our fxy, 9 minus x squared minus y squared. How do we convert to polar coordinates? Well, wherever we see a x, we're going to plug in r cosine theta. And wherever we see a y, we're going to plug in r sine theta. So doing so, we end up getting 9 minus r squared. Now, of course, one may have noticed that there's already an x squared plus y squared, and so you could just jump and substitute x squared plus y squared to r squared. But this is a systematic way for converting the integrand. Thus, if you have an expression that's x times y, for example, you now have this systematic way to convert the function. You don't always get x squared plus y squared. And our third ingredient is to use this area element and plug it in our formula above. So here we have the area element, here we have the function converted, and here we have our bounds of integration. So let's put all of these together, and we get in blue here the bounds of our integration. This came from ingredient number 1. In green here is the function converted to polar coordinates. And so that came from ingredient number 2. And so we have 9 minus r squared. In the last ingredient, the area element is here in red. So you could see how this double integral was set up, color-coded according to the ingredients. And once we have set up the integral, the rest is a piece of cake. You just integrate r as a normal variable. Okay, so what's the integral of r cubed? Well, it's r to the 4th over 4, and that's where you're getting this here. What's the integral of 9r? It's going to be 9r squared over 2, and that's what you see here. And we integrated over r, and our bounds for r is 0, 3. So we plug in for our r these bounds 0 to 3, and we would be left with this now single integral, and we carry out the computation and get 81 pi over 2. I want to emphasize here that although this r came from the area element, we distribute it through the expression 9 minus r squared just like any other r. So there's no need to discriminate between the r in the area element and the r that you would get from converting the function. So there's no need to discriminate between these two. We only show them in different colors here just to show you how this double integral is set up in polar coordinates. And to also remind you never to forget that r, just because it's not showing up in the function, doesn't mean you can neglect it. Now, a brief note on more general polar regions. So not ones that are polar rectangles, but could be more general, as we see here. Well, perhaps we could bound this region by discussing a outer function h of theta, so r is a function of theta, and an inner function, r is a function of theta g theta. And the bounds of the angle on our angle theta of alpha and beta, so that we could set up our double integral for more general regions this way if the region is described in the manner you see here.